Hey everybody, we're going to continue talking about our second standard, which is on graphing and identifying key characteristics of polynomial functions. So we're going to be looking today at how this intermediate value theorem, which is a new theorem for us, but it's going to connect the idea of finding zeros using synthetic division and what our graph looks like. So it's going to help us link those two things together. So how can we use synthetic division to find our zeros and how that looks on our graph? So let's go ahead and get started. I hope you got your notes with you. All right, so we're going to be starting with something called the intermediate value theorem, which I have decided to abbreviate the IVT just in our notes here. And I want you to write this definition. Okay, so I'm going to give you a moment to write it. After you write it, unpause the video and we will read through it and start to understand it together. So go ahead and pause now just to write it down. All right, so hopefully you've got that written down and you've unpaused. Here we are again. If f of x defines a polynomial, okay, which means it can't be a rational function, all right, it has to be this polynomial thing we're talking about, and it only can have real coefficients, so it can't have any imaginary coefficients that we've seen before. Okay, doesn't mean that there can't be imaginary solutions, but the coefficients inside the polynomial are all real numbers. And if a and b that we're talking about are real numbers, and the values of f of a and f of b are opposite in sign. So let's stop right there. So we're going to be talking about a, which is an x value, and f of a, which is a y value. Then we have also b and f of b. So we have an x that gives us a y, and another x that gives us a different y. Okay? If these are opposite in sign, now the a's can be whatever they need to be. A and B can be whatever. The x's. It's the y values that are going to tell us something very important. They're going to tell us if there exists a real zero between the x's. So let's draw a picture. Let's suppose we have A right here and B right there. And f of a is right here. So that's the value. So this ordered pair is a comma f of a. And then we've got b, and then we've got f of b, which is the y value that goes with it. So this ordered pair here at the bottom is b comma f of b. So what this says is if f of a and f of b have different signs, as in one is positive and one is negative, as in one is above the x-axis and one is below the x-axis, because that's what we know to be below, to be positive and negative. Now it could be reversed. I could have a negative then a positive. I could have below and then above, but we're looking for them to be different signs. Then there must be at least one real zero between A and B. That means that somewhere in between there must be a zero. There must be an x-intercept. Think about why that must be. Why does there have to be a zero that falls between A and B if the y values, one is positive and one is negative? I'm not going to answer that for you. I want you to think about it, and I am going to ask it. So if you want to write down your answer to that question, why must there be an x-intercept between A and B if the y value f of A and f of B have different signs? One is positive, one is negative, one is above, one is below the x-axis. Write down your answer because that's my first question when we get back together. All right, so we're going to be using synthetic division because we know that if we use synthetic division for f of 2, that we get the y value as the remainder theorem. So we want to know that there's a real zero between the 2 and the 3. So we're looking on the graph and there's the 2 and there's the 3, and we want to know that there's a real zero somewhere in between there. We don't know where, but we think that there's one between 2 and 3 on the x-axis. And we will use synthetic division to show this. So I'm going to find f of 2. Ooh, I don't know what happened there. Okay, by using synthetic substitution. 1, negative 2, negative 1, negative 1. We get a 1, 2, 0, 0, negative 1, negative 2, negative 3. Now, I didn't expect this to come out to be a 0 because I'm not looking to see if 2 is a 0. I'm looking to see if there's a 0 between 2 and 3. So it's okay that this came out to be a negative 3 and not a 0. So we would say that f of 2 equals negative 3. Now let's test f of 3. 1, negative 2, negative 1, negative 1. 1, 3, 1, 3, 2, 6, 5. All right, so f of 3 equals 5. So there is a 0 between 2 and 3 because f of 2 is negative and f of 3 is positive. So it is true that there is a 0 between 2 and 3. It crosses the x-axis. You have to think about why. Let's try another one. We're going to use synthetic division here to show that there is a 0 between 3.7 and 3.8. So you might want to grab your calculators for this one because we're going to do a little bit of multiplication. So have your calculator ready to go. Pause the video if you need to grab it. And let's go ahead and try to find f of 3.7. So we'll set up our synthetic division. And let's find 3.7. So I need 3.7 times 1.7. And we'll subtract 2 from that, and I get 4.29. And we'll multiply that times 3.7, and I get 15.873. And then I have minus 18, because I'm adding those together. And that gives me negative 2.127. Should have written my 5 a little farther away, times another 3.7, and it gives me negative 7.8699. And I've got a positive 5 there. So f of 3.7 gives me negative 2.8699. Let's try f of 3.8. Let's see, I learned that I need to make these a little bit farther apart. Okay, we'll try it again. And I get a 3.8, and I get a 1.8, and 3.8 times 1.8 gives me 6.84. Keep going. So f of 3.8 equals 6.5896. So f of 3.7 is negative and f of 3.8 is positive. So there is a real 0 between 3.7 and 3.8. All right, you guys are doing great. All right, so how is this connected to the graph of polynomials? So if we were to generate a table of values for a particular function, so let's go ahead and we're going to create a table of values. So you can type this into your graphing calculator, just put it in your y equals, and let's get a table of values for that. So go ahead and pause the video and get that typed into your graphing calculator now. Okay, so maybe you looked at the graph of this thing first, just kind of see what it looks like, and you can see that it goes up and it comes back down and then it goes back up again. And then if you take a look at the table, so go ahead and look at that. And let's just kind of look to see what we've got there. I'm going to start with a negative 2, and I get a negative 65. And if we put a negative 1, I get a 24. And then if I use 0, I'm at 9. And I can see at 1, I'm at 10. And at 2, I'm at 147. And at 3, I'm way up at 540. So what I can see here is that between negative 2 and negative 1, I have a negative y value and a positive y value. So something must have occurred between -2 and -1. There must be a zero, a real zero, between -2 and -1 because it went from a negative to a positive y value, so it must have crossed the axis. Okay, so I know that. Now, if I go back and look at my graph, I think something must be going on around 0 and -1. Something must be happening, or 0 and +1. Something must be happening between 0 and 1 because it's either touching the axis or it's dipping down below. So you can use some of your zooming options and maybe change your window to kind of look a little bit closer at that part. But what I do know is that between -2 and -1, it did cross the x-axis. I don't know exactly where, but I do know that at -2 it was down at -65, but at -1 it was up at +24. And then it came down again, and I can see something's happening in here. So, can we draw this shape? Can we draw what this is going to look like? We certainly can. We can get a good image just because we know when is it above and when is it below the x-axis. So this intermediate value theorem really helps us connect the locations of these points to try to draw a picture of our graph. We're going to keep working on this, but great job, and really think about what it means for the intermediate value theorem and how we get that information from using our synthetic substitution.